Hello, in this video we are going to review kinetics. All right, so one thing to keep in mind as we're talking about energy and spontaneity of a reaction is spontaneous reactions don't always occur quickly. So you can kind of think of, for instance, ice melting. If you're at room temperature, ice melts really slowly, right? And if you lower the temperature, ice will still melt as long as you're above, its freezing point, but it melts even slower at lower temperatures. So even though ice melting is a spontaneous reaction, or a spontaneous process, I should say, it takes a really long time. So just keep in mind, a spontaneous reaction does not always occur quickly. All right, so when we're talking about kinetics, we are talking about the rate of a reaction. So you might remember that rate is equal to a rate constant K times the concentration of the reactants. So again, K is our rate constant. And the units are going to vary depending on the reaction itself and how many reactants you have. So we'll just write units are variable. And then the concentration of the reactants is in moles per liter, so molarity. Okay, so what are some factors that affect the rate of a reaction? So we already talked about temperature, right? So if you increase the temperature of a reaction, you're going to increase the rate, because if you have a higher temperature, there's more energy. Another factor that affects rate is the concentration of your reactants. So if you have more reactants, they'll have more collisions with each other, so they'll react faster. And then if you have less reactants, there'll be less collisions between those reactants, and the rate will be slower. All right, so you might also remember that there are different orders for a reaction, or different reactions. So you can have a first order reaction where the rate depends on just one reactant. You can have a second order equation where the rate depends on, let's say, the concentration of two reactants. That can also look like this. So you can have just one type of reactant squared. And then there's also third order reactions, which are a little more rare, but the rate will depend on, let's say, one of the reactants squared and a second reactant. Now remember that the reaction order is equal to the sum of the exponents in the rate law expression. So let's go over an example of reaction, and we'll try to figure out if it's a first order reaction, a second order reaction, or a third order reaction. Okay, so let's say we have the following molecule, and it reacts with this anion here, and we get the following products. So just as a quick practice problem, let's name the first reactant. How would we name that first reactant on the left? So what is the longest carbon chain? So I'm counting 1, 2, 3. That's our longest carbon chain. So this would be propane. And then we have two substituents. We have a methyl group and iodine. All right, so which one would come first, methyl or iodine? Iodine, right? Because I comes before M in the alphabet. Now, they're both on carbon 2, so we would write 2-iodo-2-methyl propane. Okay. So back to our original problem. Let's say a chemist is trying to figure out whether this reaction is first order, second order, or third order. The way they would do that is they would change the concentrations of each of the reactants. So let's say in the first reaction, they keep the concentration of 2-iodo-2-methylpropane constant. But then they doubled the concentration of, SH. All right, and then they tracked the rate of the reaction, and they found that this had no effect on the rate. All right, then in their second experiment, they keep the concentration of SH constant, and they doubled the concentration of 2-iodo-2-methylpropane. And they found that the rate doubled. So what type of reaction is this? Is it first order, second order, or third order? So this would be a first order reaction because we just saw from the two experiments that the rate equals K and times the concentration of our reactants, except we already saw that the concentration of SH minus has no effect on the rate. So the rate really only depends on the concentration of 2-iodo-2-methyl propane. Now, again, this is first order because the exponent would just be a 1. The rate and the concentration of that reactant are directly proportional to each other. Now, let's say we had doubled the concentration of this reactant and the rate quadrupled, then that would be a second order reaction because every time we double the concentration, the rate quadruples. So because the rate doubled when the concentration doubled, this is just a first order reaction. So you might remember some of this from general chemistry. You might recall that you were given problems where there were different concentrations of each reactant. One concentration was held constant. And then you tried to kind of figure out, what type of order do we have here? So now let's talk about factors that affect the rate constant. And I forgot to put in constant here, so that's the K value. So factors that affect the rate constant are temperature, so that can affect the frequency of collisions. So if you increase the temperature, you're increasing the energy of the reactants, so they're going to collide more often, and that will increase the rate constant, or the rate of the reaction. So as a rule of thumb, so as a general rule, if you increase the temperature by 10 degrees Celsius, that's going to double the rate of the reaction. All right, second, let's talk about orientation of the molecules, also known as sterics. So this is really just referring to how accessible is the reaction site. So, for instance, in the example on the last slide, we had 2-iodo, 2-methylpropane, reacting with SH-. And basically, SH- was replacing iodine in that reaction. So it was trying to wedge its way in there to the central carbon so it could make a bond with the central carbon. And then the iodine would leave. But as you can see just from this drawing, that's not a very accessible carbon. So what if we had this molecule instead? And let's say SH was trying to replace iodine again. So this just needs to come in and form a bond with the carbon on the end, and iodine will leave. So we can already see that that is a much more accessible site. So this is something we'll think about as we go forward in organic chemistry. How easy is it for the reactants to collide and react? Is there a big bulky group blocking the reaction site, or is the reaction site kind of long and more accessible? All right, then the last factor that affects the rate of the reaction and the rate constant is the activation energy. So this is from our reaction coordinate diagram. So remember, the difference between the top of this hill or barrier and the reactants is the activation energy. And really with the activation energy, You're referring to how much energy it takes to break bonds and form new ones. So how easy is it to make or break bonds? So some bonds are easier to break than others. Some bonds are easier to make than others. So that's going to have an effect on the activation energy. And if your activation energy is really, really high, then the rate of the reaction might be really slow. It could still be spontaneous. It just might be really slow. Okay. Now, one way that we can get around the activation energy problem is to use a catalyst. So if you're taking biology, you might already know a lot about catalysts. For instance, enzymes are catalysts. Enzymes help break down molecules or form new ones. So catalysts are a way to basically increase the rate of a reaction. But catalysts don't actually lower the activation energy. Let's see. So, catalysts do not lower. Oh, the activation energy of a reaction, but they do use a different pathway to perform the same reaction. Let's see, they use a different pathway to produce the products. One example is the enzyme alcohol dehydrogenase. Some people lack that enzyme, so they don't really process alcohol as well. It takes much longer to break it down. That's one example of how catalysts can help. So let's look at free energy versus the reaction progress, and we'll just think about a generic reaction where we have reactants and then a really large activation energy and then our products. So in our original path, let's say we just mix our reactants together, let it sit, and we wait a really, really long time for the reaction to progress because the activation energy is so high. Well, one way that we could speed up this reaction is to use a catalyst again. And again, the catalyst isn't necessarily lowering the activation energy. It's just using a different path to get to the products. So another example is in lab this week, which we're doing online. We're performing a biosynthesis of ethanol from molasses, and we use yeast enzymes in order to make ethanol. Well, the yeast enzymes are catalysts, so they create a different pathway for the reaction to occur. So let's just write that down. Example, in lab, we use yeast enzymes as a catalyst, sorry. To make ethanol from molasses. All right. Okay, so next time we're going to discuss reaction coordinate diagrams, but this time they'll be for multi-step reactions.